Good morning. Welcome to Friday morning at NDC. My name's James Lewis. I'm just going to sort out my glasses so I can see things. So I'm going to start with a little story about my favourite author, who's a British fantasy author called Terry Pratchett. So Terry Pratchett, he was quite a humble guy. And when he went to conventions, even though he's probably, after J.K. Rowling, he's probably the biggest selling British fantasy author. When he used to go to conventions, he used to wear a T-shirt, and it said Tolkien's dead, J.K. Rowling said no, Philip Pullman couldn't make it, hi, I'm Terry Pratchett. That was his T-shirt. So a little while ago, because he's my favourite author, I thought I'd have my own T-shirt made, along the same lines as Terry Pratchett, which I'm wearing today, right? So this says, Turing's dead, Martin Fowler says no, Sam Newman couldn't make it, hi, I'm James Lewis. I'm the other microservices guy. Now this came in handy. This came in handy a little while ago because I got sent an email. And the email said this. It said, hi James, how are you? From Jacob. I thought, this is exciting. It's Jacob from NDC. I haven't heard from him in ages, right? And it's been 2 years. We've not been doing much face-to-face. We've been doing the live streaming and that. I thought, brilliant. And this was the next line. Sam Newman can't make it to NDC Oslo, so we're looking for a replacement. Any chance you can do the workshop? To which I immediately and obviously replied, so I think I'm the first choice for this, but it could be Sam Newman, and if it's Sam, then sorry, you got me instead. So a little bit about me. So I work for a company called ThoughtWorks. I've been there a long time now, coming up to 17 years, which means I've seen lots and lots of different clients. We're a consultancy. We build software for people. These days, I spend most of my time waving my arms and wrangling CTOs and doing yoga with them and whatever CTOs do. But way back when, I spent a lot of time building things like distributed systems for banks, insurers, retailers. And a little while ago, myself and my colleague Martin Fowler, I had a sleepover at Martin's house, and we wrote a paper defining the microservices architectural style. And we said we cannot say there is a formal definition of the microservices architectural style. And then we went on to identify a set of characteristics that we were seeing sort of emerging around microservices projects around about 2011, 12. So this is the sort of the Netflixes of the world. This is the Guardian newspapers of the world. These are some of the investment banks building trading platforms and so on. And we were trying to identify the set of characteristics that we felt made these software architectures successful. And these were the characteristics, right? So componentization via services, business capabilities, decentralized data, blah, blah, blah. You've probably all seen these before. In the intervening time, my interest has sort of changed slightly. I still write software. I still write code. You'd be pleased to know, although there's no code in this. I still write code. But my interest has sort of deepened into trying to understand whether there's any underlying set of characteristics, even underlying this set. And not only underlying this set, but underlying how we think about designing organizations as well as software architectures and enterprise architectures. Is there a set of common things, a sort of root that all these can be sort of traced down to? If you look at some of these, componentization via services, business capabilities, products not projects, decentralized governance, all of these things in some way talk to the idea of decoupling, cohesion, small units of things, whether that's small teams building smaller services, organized around smaller product lines, or whether that's decentralizing our governance, pushing governance down to the people who know the most, rather than relying on the people who know maybe the least taking decisions. There seems to be something running through, some theme, underlying theme running through this. And so I'm going to take you through my journey over the last sort of few years around how I see the underlying characteristics of microservices, team topologies, and software architecture. Along the way, I'll be talking a bit about elephants and blue whales, hope that's okay. Also a thing called the Etruscan shrew, which is the smallest mammal in existence. It's about the size of my thumbnail. I'll be talking about how cities work, and I'll be talking about why Amazon, specifically AWS, is winning. So it's a bit of a journey. I hope you stick with me. You've got nowhere else to go, frankly, so unlucky. So first up, team topologies and complexity. So when we talk about team topologies, obviously this is synonymous with the, I think, canonical text now, Team Topologies by Manuel Pace and Matt Skelton, who spent quite a long time in, they're part of their root of, or spent a long time as sort of members of the London DevOps community, or the London sort of CI and CD community. And they took a lot of stuff that we've been thinking about as an industry in terms of the microservices characteristics, how to do org design, Conway's law, and put it into the great book they wrote, Team Topologies, which I love because it gives us a common vocabulary around how to think about teams. So I was at an event a little while ago. It's a terrible life I have. I was in a workshop in the Caribbean, on the Caribbean island of Anguilla. And there were a number of people there, one of whom was Melvin Conway. Now, he actually exists. He's a real person, right? I thought he was a myth, Mel Conway. Well, it turns out he's an older gentleman, but still active and still interested in software. He came to this workshop, and in this workshop, one afternoon, we had an open space where we were talking about the uses that we'd put Conway's law to. And there was someone there from Netflix, and the person from Netflix was saying, well, actually, we design our entire building around Conway's law, right? So we have our UX teams sitting at one end of the building, then we have our platform API teams, and then we have our microservice teams, then we have the infrastructure teams. The idea being, if you don't need to speak to someone on a day-to-day basis, they sit further away. And if you need to speak to someone quite often, they sit close to you. So you can have that sort of serendipitous communication. Obviously, this is in the before times, slightly different in the after times. So we were at this event and we were talking about this. Mel Conway was, he wrote this paper back in the late 60s, right? He couldn't believe that these giant sort of, billion-dollar unicorns are organizing themselves according to the principles of the law he sort of wrote down around organizational design, mirroring software architecture, the mirroring hypothesis in 68, 69. There was something else that came out of this meeting, someone else who was working for AWS who was there. And they said this: the bigger we get, the easier it becomes to get bigger. I can't tell you who it was, Chatham House rules and all that. But they sort of said, they made this statement. And as AWS gets bigger, it's easier to get bigger. As we add more people, it's easier to add more people. As we add more products, it's easier to add more products. In fact, they said, the only limit is our hiring. The only limit to how big we can get and how fast we can go and how many products we can release is the number of people we can bring in and on board. I mean, is that usual for big companies? Because they're a pretty large organization now, right, AWS. How many of you in the room work for a large company? I mean, over 1,000 people. There's a few of you, quite a few of you. How many of you would say, as you add more people, it gets easier to add more people? There's one person sitting at the front, standing at the front. One person. This sort of flies in the face, really, of common wisdom around how we scale teams and scale organizations, scale our software. The received wisdom is the mythical man month, right? It's the idea that as you add more people, the slower we get because the communication overhead increases. So I was intrigued by this, and I started looking into why this might be. What are AWS doing, and other organizations, as we'll see, that enables them to do this? That as they scale, they get this effect where they get faster and bigger more quickly. So I'm going to talk a little bit first about value and flow. So my belief is that the goal of a successful organizational design is to optimize the flow of value, right? All else is subordinate to that. What do I mean by that? It's to optimize the idea of product, the ideas from product people, the ideas from our business, and to be able to easily and quickly flow those ideas through into some kind of production state. And I think that's true for anything, whether that's digital products, whether that's physical products, whether that's an orange being transported from a field onto a supermarket shelf and into your house, or if it's just a website, a feature being built and delivered on a website. I quite like this quote from Daniel Terhus-North. The goal of teams and optimizing teams and self-reflection in teams should be to safely and sustainably reduce your lead time to thank you. Right? I like the thank you bit. It's not enough to just get it into production. Someone has to be happy it's there, right, and say thank you at the end. So this is the idea of flow, the flow of value from idea into making money, saving lives, whatever it is. But that does beg the question, what do we mean by value? Incidentally, I've got conference coffee. I was really looking forward to terrible conference coffee. It's actually quite good here, which is rather disappointing, actually. Cheers. What is value? What do I mean by value? Well, value can be anything, really. It's stuff. It could be physical goods. It could be products being shipped through, onto a supermarket shelf and into your home, or it could be digital products. Essentially, they're kind of the same thing. Like, an item of clothing that Zara is selling versus, the feature I'm deploying on my, on my government website or whatever it is, they're kind of the same thing in some sense, because all they are is stuff, raw materials. In the case of what the majority of us do day to day, it's digital raw materials, if you like. It's bits. We're going from, an idea that someone has, and we're adding more and more information to that idea as it progresses through a value stream until finally we deploy that idea in some concrete form into production. Whereas, for example, for Zara, that's going to be an item of clothing, but they're the same thing. Zara, there's a designer, or any clothes retailer, there's a designer who's going to do a design. They're going to, put their pen down. That design gets then sent to a manufacturing facility. The manufacturer makes it, and it progresses through a series of warehouses via lorries until it's in a shop and you buy it. If you squint, everything, all these systems pretty much are the same. Raw materials and being optimized, the flow of value into production, or some form of production. Incidentally, Zara, amazing organization. I don't know if you've read anything about them, but from, they're not far north of here, in A Coruña, aren't they? The head office. I was there for a little while. They can go, the designer puts the pen down, 15 days later, that design is being sold around the world. That's a pretty cool supply chain, isn't it? 15 days from pen down to in the store. So what is value? Value, I think, is anything, right? Anything that gets progressively, moves through this sort of value stream into some production-like state. But the question is how long it takes. And as I said, with Zara, they optimize their supply chain such that they go from pen to store in a really, really short period of time. Often, the organizations we work in, certainly in big organizations, they've accrued lots and lots of sort of scar tissue over the years. So that value stream, that value chain of getting from idea into production can take a while. This is a real value stream map up here. This is how long it takes to go from idea to production for a single line of code in a retailer in the UK. That's not a short process, right? This is not a short process. Incidentally, this laser works. That blue square there, that's writing code, that is. All the rest of it is all the other stuff that's accrued around how they get stuff done. Apologies if this looks like a bit like your own value streams, but you've got system integration testing, UAT, performance testing, regression testing, service handover, etc., etc., etc. And up this end, you've got requirements, development into documents and options and selections. And this is my favorite bit here, where these are two sets of data architects. They've each got their own canonical model. Don't think they know what canonical means. And they just update each other's and go around in a circle for weeks. Brilliant. Adding value there, right? So how long does stuff take? Often, it takes quite a long time. Many organizations have value streams that look like this. So why is it that I think team topologies are so interesting? Well, Team Topologies, the book Team Topologies, it identifies a set of team structures that help us to optimize for the flow of value. Talk explicitly about 4 different types of team. We talk about stream-aligned teams. So understanding what your value stream looks like and organizing teams around those products. The products, not projects. Long-lived stream-aligned teams. We then have enabling teams. Enabling teams are those sort of scarce resources that we can't get enough of. There's never enough security engineers. There's never enough user researchers. Right? How do we use those most effectively? We use them as consultants in enabling teams. We have complicated subsystem teams. There's this really gnarly kind of risk management thing down here. We might need a team to work just on that because they're going to build up the knowledge to do so over time. And then platform teams who provide tooling and a platform to enable the other teams to go faster. So bear in mind, this is the Team Topologies setup. So what about software architecture and complexity? Because I had 3 things in the title: software architecture, team topologies, and complexity science. I'll come back to this quote. The bigger we get, the easier it becomes to get bigger. As I said, Fred Brooks, this is the received wisdom. Adding manpower to a late software project makes it later. Because at a certain point, the information flow, the increased overhead of communication between people means you slow down, means you get slower. This was true many years ago, and it's still true in the majority of cases now. I mean, who identifies with this statement still? Yeah, majority of the room's putting their hand up here. And this is why I was thinking this is so interesting. So I went away when I heard this statement from the person at AWS, and I put some numbers together. So pseudograph. Any data scientists in the room? Yes, there's not many data points on this. It's all that were publicly available. And what this is, this shows AWS's growth in terms of people. It's actually Amazon's growth in terms of people and growth in terms of revenue. This is plotted log. And what we can see, the 0.49 doesn't really mean anything, but the 1.15 exponent on that line, on that graph, it means that Amazon indeed are growing faster than they should. As they add more people, as they double in size, they more than double the revenue they're generating. As they're adding more people, they're more than generating the revenue that they should. This is not usual. As we double in size, normally what happens is we slow down a bit and we don't generate exactly double the revenue. We generate slightly less than that. And I'll come on to that and why in a moment. So again, why is this? Why are Amazon doing this? How are they doing this? And I thought back to, the famous memo from Jeff Bezos, 2004, I think it was, where he issued a set of directives, if you like, a set of constraints on how Amazon was going to operate moving forward. Some of these include teams must communicate via interfaces. Right? We're not going to communicate via databases anymore. We're not going to fertile with each other's privates to murder the old C++ joke. But we're going to communicate instead via APIs, clearly defined APIs that are externalizable. All interfaces, I must be able to sell. I must be designing the interface to my team as if I was going to sell it to someone else. And then finally, the famous one, 2 pizza, or we'll come on to it, Dunbar's number teams, limiting team size. So these are architectural, team organizational, and organizational design constraints that were imposed on the Amazon organization way back when, way back in early 2000s. Is there something about these constraints that's meant they're now growing faster than they should? Faster than most of the rest of organizations on any of the exchanges? I think what they did here, what Jeff Bezos did, is he implemented, or he encouraged Amazon to implement a set of forcing functions for flow, a set of forcing functions to maximize the flow of value from idea through into production, whilst limiting the blast radius, while limiting the size of the architectures, the systems that his teams were building. So limiting interactions to nearby teams. Go back to that Netflix example, sit next to people who you need to speak to a lot. Team isolation. In the same way that we want to decouple our software from other software and have cohesive software, we want to do the same thing with teams. It's Conway's law again, and the mirroring hypothesis. When we talk about teams, we also talk about architecture. And we scale by this idea of Dunbar's number, which is a social construct, which I'll come on to in a second. So talk a little bit about team topologies, talk a little bit about software architecture. But what do I mean when I talk about complexity? So this is something I sort of went down the rabbit hole on some number of years ago. This topic of complex adaptive systems. So complex adaptive systems, they came out, if you like, from this institute called the Santa Fe Institute, which is in New Mexico. And it's no coincidence it's in New Mexico, because Santa Fe is quite close to Los Alamos, famously where the Manhattan Project was run, now still the national laboratory in the US, one of the national labs in the US. And a lot of the folk working in Los Alamos on things like chaos theory, and before that on things like Monte Carlo simulations, von Neumann, he invented Monte Carlo at Los Alamos to model plasma physics in exploding or imploding cores, actually. A lot of those folk got interested in this idea of chaos theory, complexity, and they set up this institute called the Santa Fe Institute for the study of complex adaptive systems. So what do we mean by complex adaptive systems? Well, pretty much, complex adaptive systems are anything. Everywhere you look, you see a complex adaptive system. Every biological unit you look at is a CAS, complex adaptive system. The organizations we work in are complex adaptive systems. The world in which we live, the cities in which we live. And mice and elephants are complex adaptive systems. So this graph shows the body mass per kilo. It's basically the metabolic rate of mammals as they get bigger. And the interesting thing about this graph is you see the straight line. When you actually look at the exponent of this graph, what you find is the exponent of that line is the x to the is 0.75. What this means is that metabolic rates in mammals, they follow this thing called a scaling law with an exponent of 3/4. It's a bit weird, but as you double the size of a mammal, it only needs 75% of the calories that you think the mammal should need. So as you go from, a dog to a small pony, I should work out what's twice as big as a dog, really. As you go from one thing to a slightly bigger thing, or double the size of a thing, it doesn't need to eat twice as much food. You think it would. It needs to eat, or it needs to take in 75% of the calories in which it should. There's another scaling law out there in terms of companies, organizations. If you look at, sort of doubling the size of organizations over time, as you double the size of organizations, the revenue that they're taking, you see a similar pattern, a similar scaling law. This is from NASDAQ 100. And what you find here is, again, the slope is 3/4. The vast majority of organizations, of companies, as you double in size, you get 75% of the revenue out. It's a similar scaling law. Revenue scales with the number of employees following a scaling law of about 0.85. As you double in size, got the 75 wrong, sorry, 0.85. 85% of the revenue out. Similarly, if you look at another complex set of complex adaptive systems, which are like cities, conurbations. If you look at the cities of Utrecht and Rotterdam, for example, which are roughly double in size, what you find is, as you double the size of a thing, you go from a village to a small town, to a bigger town, to a city, to a mega city, etc. The spending on infrastructure only goes up by 85% as you double in size. You only need to get 85% of the water pipes, the sewage pipes, the electricity pylons, the number of petrol stations. It's not double the number of petrol stations as you double in size, it's 85%. Infrastructure scales with population with an exponent of 0.85. So at this point, you're all thinking, great. Well, I started off talking about software architecture and teams and organizational design. What on earth is he talking about now? Well, what I'm talking about is coming back to the set of underlying characteristics. Because whenever you see straight lines across lots of different areas, you should be asking yourself the question, what is the same about these things? Are there any relations between them? That's really at the heart of science. Geoffrey West puts it very well. He says, quantities that do not change when other parameters of the system change, they play a special role in science. It's a great book. It's at the end of, as a reference, but Scale, the Universal Laws of Life and Death in Organizations, Cities, and Companies. And what we're talking about here is this concept of economies of scale, right? This is what our CFOs love, right? This is when we need economies of scale. You know, as we get bigger, we're going to get economies of scale. We'll sit certain people together, economies of scale, et cetera, et cetera. And what economies of scale really means technically, from an economics perspective, is if you have on a log-log graph linear scaling, this straight line, as you double one number, you double the other, economies of scale means you get this concept of sublinear scaling. As you double one number, you get less out on the other axis, less than you'd expect. And the cities, mammals' metabolic rates, and organizations, they all exhibit, as they scale, this idea of sublinear scaling, sub-exponential growth. So what's that got to do with complex adaptive systems? Why am I telling you all this? Well, this idea around sublinear scaling can be explained by a set of very simple characteristics. Mathematically, there's mathematical proofs around this. This idea of self-similarity, the idea of self-organization, complexity, and emergence. So what do we mean by self-similar? So self-similar is, for example, cells in the body of a horse and a human. They are self-similar to one another. Self-organization, apart from the DNA, you go from this incredibly simple single cell to this complex mammal, and it's a self-organized growth pattern, basically. You get complexity, by which we mean the whole is greater than the sum of the parts. If you run the same thing twice, you don't get the same results twice. And the idea of emergent behavior. Now, how does this relate to things like teams and software? Well, if you think about when we're writing software, when we're on teams, every single time we write a piece of software, right, we're building a complex adaptive system within a complex adaptive system. If you take one component out, one person is ill for a day. If you take one person and swap them for another person, we're going to get a different outcome at the end of it. It's a classic example of a complex adaptive system. And these CASs, these complex adaptive systems, they can be explained mathematically by these three simple principles. The first one is the idea of space-filling fractal networks. So in this case, I've got a hierarchical space-filling fractal network. So an example of this in mammals is our circulatory system. That is a space-filling fractal network. An example of this in an organization is the communication pathways through the hierarchy of the organization, or if you like, through the value streams, how the work is flowing. The next thing is this idea of invariant terminating units. I'm trying to get our staffing folk in ThoughtWorks to stop calling us resources and start calling us invariant terminating units instead. I think that's a much friendlier term, I mean, it's better than meat bags, which was also on the table at one point. But this idea of invariant terminating units in companies, that's people doing work. In organisms, it's the cells. And in cities, it's things like the houses that people live in. And then this idea of optimization. Complex adaptive systems are able to self-optimize based on feedback. So in the case of cities, the feedback is sort of based on economics, as it is in companies. In mammals, it's based on evolutionary feedback over time, selective processes. So complex adaptive systems, they're everywhere. We're in one now. We live in them. We work in them, and we are complex adaptive systems. And they can be described by these three principles. The key thing is that these three principles explain these scaling laws that we showed. Hierarchical fractal networks, they scale following a power law with an exponent of less than 1. As you double, anytime you have a hierarchical fractal network, as you double the size of a thing, city, organization, mammal, you need less than you think of in terms of calories, less than you think in terms of infrastructure and so on. And that's dependent on the hierarchy. And incidentally, they're self-similar across scales. So Walmart and a convenience store, they're the same. They're just different sizes. I'm going to talk a little bit now about corporate metabolism. So why does revenue growth slow as size increases? I showed this graph a little earlier. So as you double the size, you don't get double the revenue. Why do metabolic rates slow as size increases? So as you double the size of a mammal, you don't need double the amount of calories. The reason is the metabolic rate of the mammal slows down. And it's down to this idea of something called back pressure. So in any hierarchical fractal network, what you end up is this idea of self-optimization, where you have bigger things turning into smaller things. If you look at our circulatory system, we have a heart, then we have the aorta. The aorta splits into two arteries, splits into more arteries and more arteries and more arteries. Every time those things split, evolution has optimized us so that the artery, the cross-sectional area of the arteries add up to the same cross-sectional area of the arteries they split from. And the reason is kind of obvious when you think about it. The reason is if you didn't do that, you'd get essentially a turbulent flow where the arteries split. So when our blood is pumped out from the heart, goes into an artery, and it gets pumped through all the arteries to our cells and back again. If you didn't have this idea of equal cross-sectional areas, as the blood hit a split in the arterial system, there'd be back pressure, putting pressure back up on the heart, causing the heart to beat, to do more work, which we've optimized out of because it basically gives us heart attacks. This is why plaque buildup is a bad thing, because it narrows the arteries and it stops them acting so efficiently in terms of the cross-sectional areas and back pressure. Essentially, when we go from one thing to a smaller thing, in complex adaptive systems, in hierarchical fractal networks, what we get is the one thing splitting into two equally sized things that add up to the one thing. And this is true in cities as well. So we'll get a big water pipe coming into the city, which splits into smaller water pipes, into smaller water pipes, into smaller water pipes till it hits our homes. The homes are the invariant terminating units. This is true in companies as well, in terms of the infrastructure that they have. And this is all implied by hierarchies. So hierarchical fractal networks basically explain the metabolic rate changes in mammals. If you look at a mouse and you look at a whale, essentially at the bottom, the cells are the same size, right? These are these invariant terminating units. The only difference between these two animals is the depth of the circulatory system, the depth of the hierarchy, if you like. Right? And that depth of hierarchy, the number of levels in the hierarchy, that gives you this metabolic rate decrease. Here's a fun fact. Elephants and blue whales, they don't get cancer. Why don't they get cancer? Well, because they operate so slowly, their metabolic rates are so slow that the cells don't have enough time to develop mutations to get cancer. That's how slow the metabolic rate is of an elephant and a whale. They operate really, really slowly. So if you're an elephant looking at humans running around, you're seeing people just go in the same way that when we look at a mouse, the mouse seems to be running around really, really fast because their metabolic rates are so much faster than ours are. Consequently, they also live for different lengths of time. Mice live for a really short period of time. Whales, elephants live for a really, really long length of time based on metabolic rates. So bigger animals, it turns out, are more efficient because they've got this deep hierarchy of circulatory system and their metabolic rates are much, much slower, and so they turn out to be more efficient. They don't need as many calories as smaller animals. This is down to this idea of impedance matching in the circulatory system. The hierarchical networks split and branch and branch and branch and branch until you reach some cells. And this is driven by feedback from evolution. This is also true for companies. When your CFO says, economies of scale, we want to be more efficient, bigger companies are more efficient because they've got these deep hierarchies of infrastructure. Infrastructure cost scales at 85% as you get bigger. But they also develop deeper hierarchies as they age. They develop deeper hierarchies of infrastructure and deeper hierarchies of information flow. And they optimize based on feedback from market forces. But the key thing is, both mammals and organizations slow down as they get older. So I'll come on to a bit about flow now. I showed that value stream map earlier. If you sort of take one of these ideas of a hierarchical network, hierarchical fractal networks, you can think of a value stream as one slice through the hierarchy, the information hierarchy of an organization. And so when you've got these really long value streams like we see here, or like I showed earlier, what that's showing you is that there is a really deep hierarchy through which information has to flow. There's a really deep hierarchical network. And the other thing you do when you do things like plot value streams is you start to find things like queues. You start to find where the information flows start to split and where back pressure is building up. So queues in our organizations, queues of work, queues of ideas, that's essentially the same as plaque in mammals' arteries. Whenever we have a queue, it's putting back pressure up on the informational sort of hierarchy of an organization, slowing stuff down. It's making the organization work harder, slowing things down. Don Ronderson, in the Principles of Product Development Flow, anyone who was in my talk yesterday would have heard me talking about this. He talks a lot about queues. He talks about the impact of queues on the work that we do. And he talks about this idea of impedance mismatching. The idea that as information's flowing, it's being blocked, it's being stopped. It's building up in these sort of backlogs, essentially. And, think of software developers. We all know queues in messaging systems. If a queue's backing up, that's not a great thing, right? It's putting back pressure up the system, and, it shows that the downstream systems aren't able to keep up with things that are happening. So, to recap on corporate metabolism. As companies scale, they add more and more processes and hierarchy. As we get older, we add deeper and deeper hierarchies in terms of information flow. Our value streams extend and extend and extend. Oh, we had this problem in production one time. We better put in a 6-week UAT period or 6-week regression period. Suddenly, you've got an extra 6 weeks before anything can happen. You add more processes. As you add more people, how do we manage these people? Well, we'll add more people in to manage. We'll add deeper and deeper and deeper hierarchies. Every time we add hierarchy, the math shows that things will slow down. Our metabolism, the corporate metabolism, the team metabolism, slows with hierarchy. That's just inescapable. It's physics. It's maths. There is maths to prove that. Things slow down with hierarchy. But we also, as I said, deliberately block our corporate arteries by adding in these queues, by having lots of stuff building up, waiting to get done. It's putting back pressure up on the corporate heart, if you like. It's a bit of a sidebar. Can we identify when this is happening? Another great book, seminal book really, is Accelerate by Nicole Forsgren, first author, Jez Humble and Gene King, which summarizes the state of DevOps reports over the years. And in that, they identify 5 key metrics that we can use to identify whether our organization is performing well or not, whether our teams are performing. We've probably come across that. Here's a fun fact. As a result of this research, who in the room has got a change request board that they have to talk to, or an architecture review board? Got 1, 2. Is anyone listening? Excellent. People are still listening. That's good. There's a few hands going up. The research from Dora that summarizes Accelerate, it shows that change request boards predict low performance. And I use that term precisely. If you have a change request board or an architecture review board, it's a predictor of you being a low-performing organization in terms of IT. It's not correlated with, it predicts it. And why is that? It's because every time we put something in, like a change request board, we're again blocking the flow of information. It's basically like, we're deliberately stopping the heart beating every now and again before letting it start again. So, can we do this? Can we use these metrics to monitor organizational health? Well, these metrics mean time to recovery, cycle time, change failure rate, number of deploys, and now I think they call it scalability. I'm going to say I can't remember what the final one is. By monitoring these, we can actually understand how fast we are going, what our metabolic rate is as a team, as an organization. We can identify how old we are, if you like, and if we're getting older or if we're getting younger. So I think we can, by using these. They're the equivalent, really, they're leading indicators of organizational health. They're the equivalent of going to your general practitioner, your doctor, and them taking your blood pressure and your pulse, your temperature. It's not going to tell you exactly what the problem is, but it's going to give you a pretty good idea of whether you're sick or not. And as I say, they're leading indicators, and that's super useful. It's like monitoring heart rate and blood pressure. And so we should work to improve these. Daniel Tirhurst North, he has this lovely phrase, as I sort of quoted at the start, working to safely and sustainably reduce lead time to value. That's what he means. We're working safely and sustainably to improve these metrics, to get stuff out into production and people saying thank you more effectively. Working on flow efficiency, but, and it's a big but, doesn't matter how good you are at these, you're still going to be limited by the hierarchy in which the organization has. You can only improve to the point that's imposed by the hierarchy, the hierarchical fractal network that makes up the complex adaptive system, which is the organization. Next up, organizational mortality. So it turns out companies die, right? All the time. The half-life of a company a listed company, any one particular company, on average the half-life is 10 years, 10 and a half years. There's 50% churn every 10 and a half years, right? Companies get taken over, they go out of business, they become insolvent, they go bankrupt, etc. Why is that? Well, it seems that as companies age, not only do they get slower, but they also do some other things. They tend to spend less money, they make less investment in terms of research and development. The thing that made them successful at the beginning is no longer as important. The product development, the innovation, that's subordinated to the hierarchy, to cost efficiencies, to savings, to being like managing risk and governance and these things. They lose track of what made them successful to start with, what made them young, if you like, the investment in the products, the flow of getting those products in front of their customers, and making them happy, making them say thank you, or hopefully having them say thank you. So as they get older, they spend less money on R&D. And you end up with more hierarchy, usually. More processes, more constraints. And when you put these two things together, what you end up with is this idea of, like humans, as we get older, we have more constraints, we get plaque buildup, eventually we die. So too true for companies. So with companies' hierarchies, they tend to grow and grow, and at the end of it, they die. So hierarchies, hierarchical organizations, or any form of complex adaptive system with a hierarchy in it will gain economies of scale for infrastructure, right? About 0.85%. As you double the size of a company, you only have to spend about 85% on infrastructure. But they also achieve sublinear growth in revenue, about the same numbers. And over time, the metabolic rate of the company reduces, and eventually, in general, organizations will die. Sorry, that's the sad bit. I'll go on to the good news next. So scaling complex adaptive systems. There's another type of scaling law associated with growth. We talked about sublinear scaling, which is where you double the size of one number and you don't get double out of the other one. There's something called superlinear scaling, scaling in advance of the exponential. As x doubles, y increases by more than double. And if you go back to what I was saying about Amazon at the start, that's kind of what that exponent was, 1.15. And cities exhibit both types of scaling. Cities achieve superlinear growth for socioeconomic effects. Innovation, wages, professionals, crime, disease, pollution. As you double the size of a town or a city, you get more than double the amount of increases in these things. All the socioeconomic factors, they scale superlinearly, while infrastructure scales sublinearly. Turns out, have you ever noticed if you're walking around a big city, everyone seems to be walking faster? It's actually true. There's been research done based on mobile phone data by MIT, and as you double the size of a town, people walk faster with an exponent of 1.10. They walk 10% faster as you double the size than they should, up to how fast your legs will go. Yeah, which is it's just pretty cool, isn't it? So what is it about cities? What are these socioeconomic? What's the underlying reason that these socioeconomic factors scale superlinearly? Well, it's about small world fractal networks, a different type of fractal network. We talked about hierarchical networks, small world networks like social networks, like the networks you have with your friends and family, like basically every Zoom call that you had with your mates, right? Right? These are small world networks, where you have highly connected nodes and slightly more loosely connected nodes. Does anyone recognize these numbers? So these, I mentioned at the start, these are Dunbar's numbers. So we often think of Dunbar, it's a set of research into the number of connections, if you like, that people hold, and the closeness of those connections to them. We often think about this Dunbar number of about 150. That's the most commonly sort of understood Dunbar number. And actually, ThoughtWorks, we'd scale our offices by the Dunbar number of 150. Any more than about 150 people, and you don't really know them personally anymore. You know, you can't sort of say, you know, oh, hey, Jake, how's the kids, and all that kind of stuff, you know. How was the golf trip this weekend? They become sort of faceless. So if you scale by Dunbar's number, about 150, you tend to know everyone in the same office as you. But Dunbar's number, there's a range of them. It goes from 5 all the way to 500. 5 is like your nuclear family, which is a bit awkward, because I've got 4 kids. There's 6 of us. So either I love one of my kids less, or my wife, which is a bit tricky. But about 5, up to about 500. And these are your nuclear family, then your extended family, then your close friends and acquaintances, then the sort of, the set of people you might be able to rely on, then the set of people you've probably got in your phone book or something. And these networks, socioeconomic, small world fractal networks, they drive this idea of returns to scale. So on the one hand, we've got hierarchies, and they drive sublinear scaling. On the other hand, we've got small world networks, which drive superlinear scaling. How is it that this works? Well, with hierarchies, you've got no real option but to increase the depth of them, right? Information flows in one way. But with small world networks, and you see this in cities, you can add little bits on the outside, and a little bit more on the outside, a little bit more on the outside. So that they sort of grow by adding little pieces. I know there was a talk on fractal architecture, I think, earlier in the week. I've got this idea that you should be able to actually measure the fractal dimension of an architecture, because fractal dimension of a city indicates whether it's healthy or not. You can actually measure the crinkliness of the outline of a city, and it'll tell you whether the city is healthy or it's not. And it's because you add these new, more crinkly bits around the outside. The higher the fractal dimension, the healthier the city. Similarly, I suspect with architectures, although I've not measured it myself. So you add these little bits on the outside. You don't need to increase this depth of hierarchy. You don't need to increase the length of time it takes, for information to pass between things. So as cities grow, they gain economies of scale for infrastructure. They gain returns to scale for socioeconomic factors. They rarely die. Most cities don't die, There's the odd one. But even Detroit, which was a famous city that was in decline, is now rebounding. We know this because the fractal dimension is going up. And in fact, they get 115% more stuff, both good and bad. Higher wages, but more disease. More professionals, but more crime. But for 85% of the cost. Sounds like a good thing, really. You get returns to scale and economies of scale. So, are there any organizations out there that are taking advantage of this? Well, I think to an extent, the company I work for, ThoughtWorks, are. As we've scaled, we've created small world fractal networks by opening more than one office, for example, per country. We don't have one big office in the UK. We have one in Manchester, we have one in Newcastle, we have one in London. Similarly in India, we don't have one giant office in Bengaluru. We have a number of offices even in Bengaluru, and then we have lots of other offices all the way around. We try and scale by keeping these sort of fractal, these small world networks, so that people know each other. We take advantage of these networks. You could argue that the Spotify model is a classic example of how to scale using small world networks. How to scale teams around small bits of software, squads, and organize them in as loosely a coupled way as possible with as little hierarchy as possible, just enough to make sure communication happens. And then famously, Valve, it was leaked, their employee handbook a little while ago, several years ago now actually. And in that employee handbook, they had this picture to describe how they organize. Basically, they put it out there. We are a small world fractal network. This is how we want to organize. Zero hierarchy. It's based on it's based on personal relationships. People get to work on what they want to work on and things at Valve. And finally, back to Amazon, where I started. Coming back to this graph with Amazon's growth, this exponent of 1.15, they are clearly scaling super linearly. So why is it they're scaling super linearly in terms of revenue? As I said at the start, there's a set of forcing functions that were put in place to enable a set of small teams to operate independently from one another, often to the detriment of users of Amazon software or AWS's software. Anyone who's used any of the AWS APIs knows that you can jump from one to another and there's often no similarity at all, right? It's because the teams are completely independent. But what that means is they can add more. Like cities add suburbs on the side, Amazon just adds another little team, building another little product, and another little team, building another little product. Doesn't impact the rest of the organization. And as they do that, they get this virtual circle where the products that they build can be built on with other products, can be built on by other products. So as most companies get bigger, it gets harder to get bigger. As most companies get bigger, the metabolic rate decreases, things go more slowly, and eventually the company will die. But as Amazon gets bigger, it's getting easier for them to get bigger. And it's based on maths. If you look at the book where I started, Team Topologies, the streamlined teams independent with the other team structures that are, that are combined to making those streamlined teams go faster, those are examples of patterns for implementing small world networks in your own organizations. These streamlined teams, enabling teams, et cetera, et cetera. Fundamentally, that's what Team Topologies is about. It's about creating this socioeconomic structure based around small world networks, not hierarchies. So in summary, software architecture, Team Topologies, complexity science. I started off talking about the characteristics of microservices. The idea of decoupling, of decentralization, pushing stuff out, decision-making down to the people who know the most, building decoupled software, cohesive software, and organizing around business concerns, business capabilities. That's what we identified at the start as these characteristics. I think if you take the Team Topologies set of teams, the archetypes in Team Topologies, they correlate very nicely with what we were talking about in terms of microservices. And not only that, they also, when you look at the complex adaptive system theory underpinning it all, they kind of are almost a guidebook for implementing small world networks. So, social networks imply super exponential growth. Hierarchy, slow metabolic rate, inversion of control for teams, forcing functions for flow. These are the things we want to be thinking about to go faster. I'm going to finish there. These are all the books that I referenced during this talk. Sorry if you work in a hierarchy. I'm James. Thanks very much for your time this morning.